Welcome to the deep dive. This is where we really get into those big, complex topics and try to make sense of them, quickly and thoroughly. Today, we're diving headfirst into something that, well, it sounds like pure science fiction, honestly, but it might just be humanity's next giant leap. We're talking about the space elevator.
That's right. And our mission today is to cut through maybe some of the hype, some of the speculation, and give you the clearest picture we can of what a space elevator actually is. And crucially, why it could be such a massive game changer for getting into space.
Yeah.
But also, let's be honest, the huge, almost unimaginable challenges we still face trying to build one. We've pulled from some really fascinating research discussions with experts who are right at the forefront trying to make this happen.
Okay, let's unpack that vision then. When you say space elevator, what are we really talking about? Is it just a building that's like really, really tall?
Well, it's far more than that. Imagine a structure, a massive structure, extending right from the Earth's surface directly up into space. According to the plans the concepts researchers are working on, we're talking about something an astonishing 100,000 kilometers long.
Wow, hang on. 100,000 kilometers. Just for context, the Earth itself, its diameter, is roughly 12,000 kilometers. So this thing would be something like 8 times the diameter of the planet. That's just, it's mind-boggling.
It really is. And way out at the far end, that 100,000 kilometer mark, you'd have what they call an apex station.
An apex station.
Exactly.
Yeah.
And you're probably thinking, why on earth does it need to be that long?
Right. Yeah, that was my next question.
And that incredible length, it isn't just some random number. It's absolutely fundamental to how it works, why it exists. It all comes down to some pretty wild physics that we're definitely going to get into.
Okay, so a structure 8 times the Earth's diameter. The physics sound intense, but why? Why would we even want to build something like this? What's the advantage over just using rockets like we do now?
Right, that's the core question. The why is really all about cost and efficiency. Mostly cost, actually. Right now, if you want to launch something, anything, into space using a rocket, the cost is just staggering. You're looking at potentially hundreds of thousands of dollars per kilogram.
Per kilogram, wow.
Yeah, and that price tag often includes profit margins for the launch provider, sure. But compare that to the projected cost for a space elevator. We're talking maybe just hundreds of dollars per kilogram.
Okay, wait. Hundreds of thousands down to maybe just hundreds. That's like a, 20, 30 times reduction? Maybe even more.
Potentially, yes.
Yeah.
And that elevator cost, remember, that's mainly just the calculated operational cost, like the electricity to run the lifts. It's a fundamentally different economic model.
That's a massive difference. But what about the time it takes? Rockets get things up there pretty fast, don't they? Less than a day to orbit.
They do. Rockets are quick. You're in orbit in hours, really. The elevator, though, that's a different story. It would take approximately 10 days to get all the way up.
10 days.
Think about it. You're covering 100,000 kilometers. That's like going around the Earth 2.5 times. So yeah, roughly a week, maybe a bit more, to reach that apex station.
Okay, so huge cost savings, but a much slower journey. Is there a good way to think about that trade-off, like an analogy maybe?
Absolutely. The best analogy is probably air cargo versus sea cargo right here on Earth. Air cargo, expensive but fast. Need something delivered tomorrow, you fly it. Sea cargo, much, much cheaper, but it takes weeks, maybe months.
Right, gotcha.
The space elevator is basically the sea cargo option for space. It's perfect for bulk materials, things that aren't time sensitive, where cost is the driving factor. And that trade-off, cheap but slow, it unlocks completely new possibilities, especially when you start thinking about interplanetary travel.
Okay, tell me more about that. How does this change things for, say, going to Mars? That's always the big one people talk about.
Right, Mars. Currently, using rockets from Earth, it's tricky. You can't just launch whenever you want. The launch windows, the optimal times, only open up roughly every 26
Every
months.
2 years. Why so infrequent?
It's because we rely on the most fuel-efficient path, which is called the Hohmann transfer orbit. Basically, you use Earth's orbital velocity to give this spacecraft a kind of swing towards Mars. It saves a ton of fuel. But even using that efficient route, the journey itself takes 7 months, sometimes longer.
7 months? Wow. And that cost, what makes rockets so incredibly expensive? You mentioned fuel, but is there something more fundamental, like that rocket equation I think I've heard of?
There absolutely is, the Tsiolkovsky rocket equation, yeah. It's brutal, honestly. It dictates the relationship between fuel, mass, and velocity change. And what it tells us is just how inefficient chemical rockets are against gravity. Think about this. For every 100 kilograms you launch, something like 97 kilograms of that is just propellant, just fuel.
97%.
Yep. leaving maybe 3 kilograms, just 3%, for the actual payload, the satellite, the astronauts, the cargo. It's almost entirely fuel tank and engine. And that's with using Earth's gravity assist. If you tried to launch straight up without that orbital mechanic help, your payload fraction would plummet even further, maybe 1%, maybe even less. Costs become astronomical.
Okay, that paints a pretty grim picture for rockets. So how does the elevator bypass that? How does it help with getting to Mars?
Right, the elevator changes the game completely. First off, you could potentially have daily launch opportunities to Mars, not just every 2 years.
Daily.
Potentially. And the travel time, it could be cut down to as little as 2 months, maybe even less in some scenarios.
2 months instead of 7?
It's because you're launching from that apex station, way out at 100,000 kilometers. At that altitude, and because the whole structure is rotating with the Earth, the station is moving incredibly fast. So when you release a spacecraft from there, it gets this enormous free swing, a huge boost in velocity, what engineers call delta V. This drastically reduces the amount of extra propulsion needed to get to Mars, maybe even eliminates it for certain trajectories.
Ah, so you're using the Earth's rotation amplified by the elevator's height as a giant slingshot.
Exactly. Plus, you're not fighting your way out of Earth's deep gravity well from the surface. You're already effectively in space. It's a massive advantage.
That sounds, well, revolutionary isn't a strong enough word. Is there a way experts describe this potential shift? How big a deal do they think it is?
It really is seen as transformative. The International Space Elevator Consortium, in one of their reports, they actually called it the transportation story of the 21st century.
Wow, high praise.
And they back it up with numbers. They project that with an elevator, nearly 3/4 of space flights could be more fuel efficient than current methods. 70% could be faster than those Hohmann transfers we talked about. And get this, maybe 15% of trips could take less than 3 months. And a small fraction, maybe 1%, could be almost entirely fuel-free, just release and go.
A free ride to Mars, practically. That really does redefine our relationship with the solar system.
It makes us a truly spacefaring species, yeah. It's the gateway.
Okay, so beyond just making travel cheaper and faster, what other big opportunities does this unlock? You mentioned bulk transport.
Right, asteroid mining becomes a huge one. Suddenly, it might actually be economically viable.
Why isn't it now?
Because with rockets, you have that double gravity penalty. You fight gravity going up from Earth, and then you have to fight it again to slow down and bring materials back to Earth. For low-value per weight stuff like iron ore or water ice from an asteroid, the transport costs using rockets just kill any potential profit. But with the elevator, you could use relatively small, efficient spacecraft to shuttle between the apex station and the asteroids. Mine the ore, bring it back to the station, and then just send down the elevator. Since ore isn't usually time-sensitive, the slow elevator ride down is perfectly fine.
That makes sense. The elevator handles the expensive Earth-to-space and space-to-Earth legs cheaply. What about manufacturing? I hear talk about making things in space.
Microgravity manufacturing, yeah. That's another massive potential. There are certain high-value products, think advanced semiconductors, perfect fiber optic cables, maybe unique alloys or protein crystals for medicine that you can make with much higher quality, or maybe only make in zero gravity.
Because gravity messes things up on Earth.
Exactly. It causes defects, sedimentation, convection currents, things that hinder perfection at the molecular level.
Yeah.
In space, you remove that factor. Right now, sending the raw materials up and the finished goods down via rocket is just way too expensive for most processes. But the elevator, it makes setting up raw materials cheap. You could have factories in orbit supplied by the elevator.
Factories in orbit. Okay, and what about just pure science, exploration?
Huge impact there, too. Think about the cost of sending telescopes, scientific instruments, labs, even just supplies for researchers into space. The elevator slashes those costs. It means more science, more often, more diverse experiments. You could, for example, do large-scale agricultural studies in space, trying to figure out how to grow food for future colonists. We know plants behave weirdly without gravity, but we need way more data.
Right, you need to actually test it at scale.
Precisely. Astronaut time on the ISS is incredibly valuable, partly because it costs so much to get them and their experiments there.
Right.
An elevator could make space labs much more accessible, accelerating our learning curve about the universe and living in space exponentially.
So massive economic potential with mining and manufacturing, huge boost for science. Are there any other, maybe less obvious benefits? Anything that impacts us back here on Earth more directly?
There's actually a really interesting and potentially critical one. Nuclear waste disposal.
Getting rid of nuclear waste in space. Isn't that dangerous?
Using rockets, yes, it's incredibly dangerous. Imagine a rocket carrying highly radioactive waste exploding during launch, or failing to reach the right trajectory. It could scatter that material over huge areas. Catastrophic.
Yeah, that sounds terrifying.
But the space elevator offers a potentially much safer, controlled method. You load the contained waste onto a lift, send it slowly and steadily up the elevator, way past Earth orbit, and then release it into a stable trajectory heading towards the sun, or maybe out of the solar system entirely.
A slow, controlled ascent is much less risky than a rocket launch.
Exactly. It permanently removes the most hazardous waste from the biosphere. And, some have even speculated about using it for other waste, like plastics maybe, though the economics there are less clear. But for nuclear waste, it's a compelling potential solution.
Okay, the vision is incredible. The benefits are, well, they're almost overwhelming. Asteroid mining, space factories, solving nuclear waste. But there's always a but, isn't there?
So yes, a very, very big.
Building something on this scale, the challenges must be just monumental. Where do we even start? What's the absolute biggest hurdle?
Without a doubt, the material. Finding and then mass producing a material that can actually form the elevator's tether or ribbon. It needs to be unbelievably strong, but also incredibly light. Engineers talk about specific strength. That's strength divided by density. Strength to weight ratio. Needs to be off the charts.
How strong and light are we talking?
Think about the scale again. The tallest thing we've ever built is the Burj Khalifa, less than a kilometer high. We're talking about a structure 100,000 kilometers long.
So like 125,000 times taller?
Something like that, yeah.
Yeah.
Traditional strong materials, like steel, forget it, they're way too heavy. A steel cable that long couldn't even support its own weight, it would just snap.
Okay, so steel is out. What are the candidates then?
The leading contenders right now are both based on pure carbon nanotubes, and graphene.
Carbon nanotubes, I've heard of those. Super strong, right?
In theory, incredibly strong. Tiny rolled-up sheets of carbon atoms. The problem is making them long enough. The current record for a single, continuous carbon nanotube is something like 14 centimeters.
Centimeters, not kilometers.
Centimeters. And producing even that tiny lengths took something like 32 hours. So scaling that up to 100,000 kilometers.
Yeah.
With current tech, it would take, well, practically forever. It's just not feasible right now.
Okay, so nanotubes are maybe a distant dream. What about graphene? You mentioned that too.
Graphene looks somewhat more promising, at least in terms of production scaling. Graphene is a single flat sheet of carbon atoms arranged in a honeycomb pattern.
Yeah.
It's basically an unrolled nanotube.
Two-dimensional.
Exactly. And we've seen some real progress there. Back in 2020, for instance, LG Electronics announced they could produce graphene film that was a kilometer long at a speed of 2 meters per minute.
Okay, that's a huge difference from 14 centimeters in 32 hours.
A massive leap, yeah.
Yeah.
Still a long way from 100,000 kilometers, but it shows large-scale production might actually be possible someday.
And the idea is to make a ribbon out of this graphene.
Yes, that's the current leading design concept. A ribbon, maybe about a meter wide, 100,000 kilometers long. And it wouldn't be a single sheet. It would be incredibly thin layers stacked together, maybe over 12,000 layers of graphene.
12,000 layers. Wow.
And that composite ribbon, calculations suggest, could be strong enough to support multiple elevator cars or climbers, maybe 7 of them, each weighing around 20 tons.
Okay, so graphene seems like the best bet for the material. But even with a super strong material, there's this tension issue, isn't there? You mentioned the physics earlier.
Ah, yes, the tension. This is crucial. So the elevator center of mass needs to be placed out at geostationary orbit altitude around 36,000 kilometers.
Where satellites hang out, basically.
Right. At that specific altitude, the inward pull of Earth's gravity is perfectly balanced by the outward centrifugal force from Earth's rotation. So the net force on the whole structure is 0. It just hangs there.
Okay, balanced.
But the ribbon itself is under incredible stress. The lower part, everything below 36,000 kilometers, is constantly being pulled down by gravity. The upper part, everything above that point, is being flung outwards by centrifugal force.
So it's being stretched from both ends.
Pulled incredibly taut, exactly, like a cosmic tug-of-war rope. This means the material needs absolutely immense tensile strength resistance to being pulled apart, which graphene is potentially very good at. But here's the kicker. Because it's designed purely for tension, it has basically 0 compressive strength. It cannot handle being pushed or squeezed.
Like a piece of thread, strong when you pull it, but useless if you try to push it.
Precisely. You can't build a tower by stacking threads. And that leads directly to the next monumental challenge.
How on earth do you build this thing? If it can't handle compression, you obviously can't build it from the ground up like a skyscraper. It would just crumple.
Exactly. Bottom-up construction is completely impossible. It would collapse under its own weight long before it got anywhere near 36,000 kilometers, let alone 100,000.
So, how then? Do you build it from the top down? That sounds insane.
That's basically the plan, yes. And it sounds insane because it kind of is. The proposed method is, well, audacious. You'd first have to launch a massive spool, a giant reel carrying the entire 100,000-kilometer folded or rolled-up graphene ribbon into geostationary orbit.
Launch a 100,000 kilometers spool. Okay, that's already a huge challenge.
A massive challenge, yes. Then, from that point at 36,000 kilometers, you start unfurling the ribbon. But you have to do it simultaneously downwards towards Earth and upwards further into space
Why both directions at once?
to keep the center of mass perfectly balanced at that geostationary point. If you just unspooled it downwards, the center of mass would shift, and the whole thing would become unstable, likely falling back to Earth.
Right. Okay, so you unspool down and up simultaneously.
Meticulously controlling the speed and tension until the bottom end finally reaches Earth's surface where it can be captured and anchored. Then you continue unfurling the rest upwards to the full 100,000-kilometer length.
That sounds like the most complex, high-stakes construction project imaginable. Like, from an engineering perspective, that must be terrifying. One slip up.
Oh, absolutely. Engineers look at this plan and, while acknowledging the physics works on paper, they see the potential for catastrophic failure at every single step. Humanity has never attempted construction on this scale or using this kind of top-down balanced deployment method in space. A single mistake, a snag, a tear, a control malfunction could mean losing the entire 100,000-kilometer ribbon, an unbelievably expensive and time-consuming disaster.
Yeah, the margin for error seems non-existent. Okay, so let's say, hypothetically, we solve the material problem and we manage this insane construction method. Are we done, or are there still ongoing challenges?
Oh, plenty. We're just getting started with the operational headaches. Think about maintenance. How do you repair a 100,000-kilometer ribbon hanging in space?
Good point. What could damage it?
Lots of things. Impacts from tiny micrometeoroids or space debris. There's a lot of junk up there. Atmospheric effects in the lower sections, erosion, wear and tear. Even just high winds or storms near the ground anchor could cause stress or damage.
Yeah, and you can't just replace a section easily, can you?
Replacing the whole ribbon, if it gets significantly damaged, seems completely infeasible. So you need methods for inspection, repair, maybe reinforcement, all done remotely or by specialized robotic climbers across its entire length. A huge task.
Okay, maintenance is one. What else?
Powering the lifts, the climbers, how do they get the energy to climb 100,000 kilometers against gravity?
Yeah, that's going to take a lot of energy.
Immense amounts. One idea is transmitting electricity directly up through the ribbon itself if graphene turns out to be conductive enough over that distance without huge losses. Another popular idea is using powerful ground-based lasers to beam energy up to photovoltaic receivers on the climbers.
Laser beaming. Can that work reliably?
It's being researched, but it has challenges. What happens when it's cloudy or raining? You need clear line of sight. So you might need multiple laser stations spread out geographically, or maybe space-based power relays. It gets complicated fast.
Okay, power is tricky. What about just how the lifts grab onto the ribbon?
The attachment mechanism, yeah. How do the climbers securely grip the ribbon without damaging it, but strongly enough to pull potentially 20 tons upwards? And how does that mechanism handle oscillations or movements of the ribbon caused by wind, or even the movement of other climbers?
Slippage would be bad. Very bad.
Catastrophic, potentially. So the climber design itself is a major engineering challenge.
And down at the bottom, the anchor point.
Seems simple, but it's critical.
Yeah.
You need a massive, incredibly stable anchor point on Earth. Could be on land, could be a huge floating platform at sea, but then you have to protect it.
Protect it from what?
Well, terrorism is an obvious concern. A single, well-placed attack on the anchor could bring the whole thing down. But also natural disasters, hurricanes, tsunamis if it's sea-based, earthquakes if it's land-based. Securing that single point of failure is absolutely vital.
Wow. Material, construction, maintenance, power, attachment, security. The list of challenges just keeps growing. It really makes you wonder, who could possibly take this on and where? And maybe most importantly, when?
Right. The who is almost certainly not a single country. The sheer scale and cost, it dwarfs any project ever undertaken. We're talking multiple trillions of dollars, most likely. It would almost have to be a massive international collaboration, a global consortium requiring unprecedented levels of cooperation, funding agreements, resource sharing, ownership structures. A political and financial feat as challenging as the engineering.
A truly global effort. And the where seems pretty specific, right? You mentioned the physics.
Absolutely specific. It has to be built on the equator. That's non-negotiable.
Why the equator, exactly?
That's where the Earth's rotational speed is highest and most consistent. You need that maximum stable centrifugal force to help balance the structure and provide that slingshot effect we talked about. Anywhere else, the forces become much more complex and unstable.
Okay, equator only. That actually brings up an interesting point for where we are. Thailand seems like it's in a pretty good spot geographically, doesn't it?
It does. Thailand's proximity to the equator is a significant advantage. Plus, having access to both the Indian and Pacific Oceans could be ideal if the preferred anchor design is a mobile, sea-based platform, which many concepts favor for flexibility and security.
So potentially Thailand could be a prime location.
Geographically, yes. Whether any nation, Thailand included, has the political will, the financial capacity, and the technological base to lead or even be a major partner in such a colossal global project, well, that's a whole different question, isn't it?
Right, a big question. So we have the who, probably global, and the where, equator. What about the when? Are people actually putting timelines on this?
Surprisingly, yes. There are some ambitious targets out there. The Japanese Obayashi Corporation, a major construction giant, has publicly stated a goal of having a space elevator operational by 2050.
2050. That's only about 25 years from now.
Exactly.
Given all these challenges we've just discussed, the material isn't ready, the construction method is terrifying, maintenance, power. 2050 seems incredibly optimistic, doesn't it?
Yeah. Incredibly optimistic is putting it mildly. Most experts in the field are deeply skeptical about that 2050 timeline, solving all those fundamental engineering, material science, and geopolitical problems in just 2.5 decades. It seems highly improbable.
So skepticism is high. But do people think it will ever happen despite the hurdles?
I think many believe it's ultimately inevitable, maybe not by 2050, maybe not even in this century. But the why, the transformative potential is just too compelling, and it's driven by something powerful. A winner-takes-all dynamic.
Winner takes all? What do you mean by that?
It means that the first entity, whether the country or a consortium, that successfully builds and operates a space elevator gains an almost insurmountable advantage in space. Suddenly, they can access space resources, build space infrastructure, conduct space science, potentially even space defense, at a fraction of the cost, and with much greater frequency than anyone else.
It creates a huge gap.
A massive gap. It triggers a kind of snowball effect. Once you have one elevator, the cost of lifting the materials to build more elevators, or giant solar power stations, or orbital factories drops dramatically.
So the leader just pulls further and further ahead.
Exponentially ahead. Think about past technological revolutions. The steam engine, electricity, computers, maybe even AI now. The nations or companies that mastered them first often dominated economically and strategically for decades, even centuries. The space elevator could be like that, but on a planetary scale. The first one up basically owns the high ground, permanently changing the global balance of power.
That's a powerful motivator. It explains why, even with the daunting challenges, the race might already be quietly underway.
It likely is. And it also speaks to the unpredictable nature of progress, doesn't it?
How so?
Well, look at AI recently. Just 5 or 10 years ago, capabilities like ChatGPT or advanced image generation seemed like distant science fiction to many. Then, suddenly, breakthroughs happen. Progress accelerates exponentially.
Things can change faster than we expect.
Exactly. We often underestimate the power of focused research, investment, and human ingenuity. We don't know what breakthroughs in material science or energy transmission might be just around the corner. We don't know what we don't know. So while 2050 seems unlikely now, dismissing the possibility entirely might be foolish.
This has been quite the journey. This deep dive really shows the space elevator isn't just a sci-fi trope. It's a concept grounded in physics, facing enormous but potentially solvable engineering hurdles, and carrying implications that could fundamentally reshape our future in space, making it cheaper, faster, safer.
It truly is a monumental vision, yeah, with challenges to match.
So we've talked a lot about the practical benefits, the economics, the science, even waste disposal. But let's end on a slightly different note. A final thought for you, our listeners, to ponder. Beyond all those tangible benefits, how might the mere existence of a space elevator, a visible tether connecting Earth to the heavens, fundamentally change us? Our society, our culture, maybe even our philosophical view of our place in the cosmos. What does it mean for humanity when stepping off our planet becomes, quite literally, as simple as taking an elevator ride?
That's definitely something to think about.
Keep exploring, keep questioning, and keep diving deep. Thanks for joining us.